Can I get you to close the door? Thanks. Okay, so today we're going to shift gears, I think this is the start of a new chapter, I'm not sure, but we're going to be talking about phase diagrams and phase changes, okay? And we're going to talk about why Huntsville and Houston feel so darn hot in the summer, okay? So always try to take what's in the books and so on and also apply it to your daily life, right? Like relative humidity, okay? It's just barely mentioned in the book. So we're going to talk about that in a little bit more detail today and show how it fits in with the material. So let's discuss ideal gases, because up to this point we've been talking about ideal gases. And here are a couple of points to make about ideal gases. They're ideal because they behave perfectly with temperature, pressure, and volume. So that ideal gas law is like the perfect situation for a gas. That means that when a gas molecule hits another gas molecule, it bounces off elastically. So no matter what the energy difference is, none of the energy is lost. So that we talk about infinitely hard collisions or hard surfaces. And that means that you never get two gas molecules hitting and sticking. Because if you think about it, if you had two gas molecules and they hit and stuck to each other, now you have one gas molecule. And that's condensation. And then a third hits it and it sticks. And so now you've gone from 3 moles of gas down to 1. And eventually those congregate, make droplets, then you have condensation. So an ideal gas will not have a liquid or a solid. It's a gas. Okay, there's no way it would have a liquid or a solid because it has this kind of potential energy curve. So it has 0 potential energy between the two particles, no attractions, no repulsions, until they hit, and it goes to infinity. So no matter how hard they hit, they're going to bounce off of each other. So we don't have fusion either. So an ideal gas is kind of like the perfect situation if you want everything to stay a gas. Now, if you give water or hydrogen or neon or whatever enough energy, it'll behave like an ideal gas. In other words, they hit so hard that they don't even really realize there could have been some attraction there, some dipole-dipole forces, some instantaneous dipoles, dispersion forces. Gas molecules have so much kinetic energy that those intermolecular forces are irrelevant. Real gases, however, have those intermolecular attractions, and that creates softer collisions. And we would say they have softer surfaces. So this is what leads to condensation, freezing, and deposition, especially when you have the walls of a container. So if a molecule is going really fast and it hits the wall of the container, that wall of the container might flex a little bit, and some of that energy is lost to the wall of the container. The molecule comes off with a slower energy, and then another slow molecule hits it, and you have this attraction region. Notice this potential energy is negative. You can think of this just like a ball on a hill. If I have a ball up here and it rolls downhill, it's going to roll through this dip and out. And so as long as your average energy is above that 0 point, you're going to have good collisions and the molecules are going to bounce off of each other. But if you have a ball that's below that potential energy here, and you have another ball that comes in and hits it with just a little bit of energy, causes it to come up and then back down, they both get stuck in this region, and you end up with this is intermolecular distance. So you have a ball here and a ball here, and now you have a diatomic species. It could be a diatomic molecule. It could just be 2 molecules stuck to each other. But the point is, especially when you have walls of a container, you lose heat to the container and the system can condense. That's why it makes it so hard to do atmospheric research, really, because there are no walls in the container up above in the sky. When you're trying to do that in the lab, the walls of the container have a huge effect on your reaction rates and your experiment. So what is condensation, freezing, and deposition? Well, you know about condensation and boiling. So you boil water, it goes from the liquid state to the gas state. That'd be a phase transition. So there's the gas phase and the liquid phase. You can call those different states too, liquid state, gas state. In fact, one of the times we were hiking through the woods and we found a piece of sandstone that looked like Oklahoma. I mean, it was just looked like Oklahoma. And my daughter is older than my son. And so Jennifer, my wife, held up that sandstone and said, "Hey, y'all, what state is this?" And Katie yelled, "Oklahoma," and Thomas said, "Solid." And I was like, this is great. So they're both right. And so, yeah, gas and liquid states or gas and liquid phases. That's boiling and condensation. You have to add heat into it to make it boil. That means it's endothermic. And when you condense, that gives off heat. So that's exothermic. So condensation is exothermic. It gives off heat. Then you have melting and freezing. So you have to add heat to melt something. And so that's endothermic. And then freezing is actually exothermic. So this is solid water going to liquid water, 2 different states, 2 different phases. And then sublimation and deposition, that happens too. It's not as obvious, but if you go in the freezer and you find something that's been in there a long time and you see ice crystals that have grown on it, that's deposition. And the ice has sublimed off of your ice in your ice maker and gone straight to the gas phase and then found a little imperfection on some cardboard paper box and started to grow ice crystals on it. And so then the chances are those gas molecules hit that ice crystal, they find a nice spot to get stuck in, and they grow this beautiful, perfect crystals. And so it's kind of nice and grow snowflakes in your freezer through deposition. That's a great way to purify things too. So sublimation and deposition are a great way to purify solids. So where do these processes take place in terms of pressure and temperature and volume is what we're going to talk about. So phase transitions is really the topic of today's lecture. So we have this vapor pressure curve. If we look at the pressure of the gas above its liquid, we have this vapor pressure curve. So let's just focus on water. So on this side of that curve at lower temperatures, we have liquid water. And at higher temperatures than this curve, we have gaseous water. And on that curve, we have the equilibrium. It's also called the vapor pressure curve because that's the pressure that water will have at any of those temperatures. Okay, very good. Yeah, just send it around again. Now, every substance has different amounts of intermolecular attractions, and so they have different boiling points, different vapor pressure curves. So this is ethanol, this is ethyl ether, this is ethylene glycol, which is your antifreeze that you have in your automobile. Notice right here, 100 C, that's the boiling point of water. And so this vapor pressure curve, when it reaches 1 atmosphere, that's the definition of boiling, the normal boiling point. So this normal boiling point are those temperatures that correspond to a pressure of 1 atmosphere. So this is the boiling point of ethanol, 79 C. This is the boiling point of ethyl ether, it looks like 35. Okay, and ethylene glycol boils way up here somewhere. So this is probably over 200 C, or maybe about 150. And that's why we want to have that in our radiators of our automobiles. Ethylene glycol is the main component of antifreeze, and it has a larger temperature range. It will still take the heat away from the engine, but water would boil at 100 C. Ethylene glycol gets us 50 more degrees. So this is just the vapor pressure part of a phase diagram. What about the solid, liquid, and gas interactions? Before we get there, let's look at boiling. So we have the boiling, this at 1 atmosphere, that's what you're most familiar with. If you have a liquid like water on the stove, you turn on the heat and it will heat up, and then you start to see cavities grow when it boils. Boiling can happen even at room temperature down here, but you've got to lower the pressure. So if we pull a vacuum on water, we can get it to boil. And that's what my grad student did in terms of this cleaning study. She wanted to boil water at room temperature to pull soil out of tiny little spaces. And so this is a video from her thesis research showing room temperature boiling. Now that's not the normal boiling. Normal boiling point would be at 1 atmosphere. What temperature at 1 atmosphere? But this is room temperature boiling. And so we put soot in a capillary tube, which would be a really tough thing to clean out. And so we pull a vacuum on it and you can see the cavities start to grow and it pushes all of that soot out. So that's the cleaning part. I'm not teaching you guys cleaning, but I am showing you room temperature boiling. So you pull a vacuum on it, the pressure drops until you hit the vapor pressure of that water, and then you start to see the gas bubbles grow. These are actually called cavities. They're like holes in the liquid, and you see them grow as we pull a vacuum. They get larger and larger, and when those cavities form inside this capillary, they push out the soil. So this is a phase diagram for water. So let's start at 1 atmosphere of liquid, and we'll just warm this up. So that's 1 atmosphere pressure. That's what we experience in the lab. And whenever we hit that line, that's the melting point. Okay, so something happens. We have solid ice, and we warm it up, and all of a sudden it starts to turn to liquid. And that's the temperature at which it happens. Okay, and then we keep warming up the liquid. Then we see bubbles start to form. Then it's boiling. We boil it all away, and now we have just pure gas. And so we can label these 3 phases. We had a solid, it went to liquid, and then it went to gas as we heated it up. Now, how do we know which of these is which? Just think about that. Over here, you have a high temperature. Eventually, something's going to turn to a gas if you get it hot enough. So the one on the far right is going to be the gas. Really low temperatures, you're going to go through liquid, and you're going to get down to the solid phase. If you cool it down, it's going to freeze eventually. So down here at low temperatures, that's the solid. And in between the solid and the gas is the liquid. So you should know this phase diagram, the PT phase diagram, solid, liquid, gas, and then be able to understand what all these different lines are. So look at this week's homework. You'll see some questions related to this. Here at 25 degrees C, that's where Nethmini's research was. So when she pulled a vacuum on the liquid, you didn't see much until you got close to here and you started to see it boil. So it was boiling right here, the liquid gas equilibrium line at room temperature. So she pulled a vacuum on it and got it down to here, and all we needed to do was get down to, gosh, I don't remember what that was, 0.03 atmospheres, something like that, and it would boil. And we found that was useful for cleaning. Okay. Notice over here, this line is special. So I just put little glasses there for you to notice that line. Notice that line has a negative slope. So what that means is if I take solid ice and I press on it, it can melt. When you press on it, what happens? Well, it's gonna shrink. It's gonna take up a smaller space. It's gonna get more dense. And so this says that the liquid is more dense than the solid. And so that means that ice floats, which is really unusual. We're so used to water and ice floating in water that we think that's normal. It's not normal. But that's the only substance we really have a lot of experience with is water. And so we think that the solid floats on top of the liquid. It doesn't. It only does that in water. If you have some other substance and it's melting, the liquid's on the top and the solid's down below, and if it's opaque, you can't tell how much solid is left. Okay, so that's kind of cool. So when you're looking at a phase diagram, if this line, the solid liquid line, has a negative slope, then it's water. If it has a positive slope, it's something else. Okay. Down here, there's 3 phases in equilibrium. And so that means there's solid, liquid, and gas in equilibrium at that temperature and pressure. Okay, so that's called the triple point. Up here is called the critical point. So what's special about the critical point is that's where essentially the meniscus disappears. Notice along this line, you've got a solution in the bottom of the container, gas at the top, and you can see the barrier between. When you get up to this higher temperature, the meniscus disappears. I'll just say no meniscus. And then this vapor pressure curve, that's also the 100% relative humidity line. So whenever you want to know what the pressure of water would be at 100% relative humidity, that's what that line is. So at a given temperature, like at the boiling temperature, 100% humidity would have the vapor pressure of 1 atmosphere. Down here at room temperature, it's like 0.03 atmospheres is the 100% relative humidity. If the vapor pressure of water is below that, then we have some smaller percentage. We have like a 50% humid day or a 70% humid day. So let's do that heating experiment. This is a new slide. It's not in your notes, but you can draw these little pistons off to the side, perhaps. So over here on the left, we have a little piston. I've got a container and a piston, and it's all ice inside. So it's perfectly solid, all inside there. And we warm it up, and it expands just a little bit, but not much. Not much happens. It's just the solid heats up until we get to the melting point. At the melting point, we start to form liquid water. And ice floats in water. So you see the little ice cubes at the top, and you see the liquid water, and it will stay at that melting point until the solid is all the way gone. So in terms of a heating curve, let me try to draw that here. I've got temperature and time. So we heated the solid up, and then the temperature stays constant for a long time at the melting point at TM. And that temperature won't change until the solid's gone. That's what we mean by solid liquid equilibrium. The solid and the liquid phases are both there at that temperature until you run out of solid. If we keep putting heat into the system, then we end up with just total liquid, and we're just heating up the liquid. Notice there's still no meniscus, there's no gas in there, it's just liquid, and we're heating up the liquid. And so then we can heat up the liquid over time. So in our heating curve, we're turning up the temperature over time. And then when we get to the boiling point, then we start to see bubbles, and we start to form the gas phase. And that will sit at T boiling until we run out of liquid. So this is called a heating curve over here on the left. It'll bubble, 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 and then the liquid level will drop until it completely goes away and you've boiled away all the liquid. Now you can just heat the gas. And so over here, notice it's really expanded a lot, and we're just heating up the gas, and then you'll end up with like an ideal gas in the container. Okay. And so then up here, the heating curve will just continue on, and you're just heating the gas and making it hotter and hotter and hotter. Okay. So the heating curve, little piston diagrams just showing you the volume expands mostly when you go to a gas, very little volume change in going from a solid to a liquid. And you see that those pauses in temperature occur at the melting point and the boiling point. Okay. Any questions on this? This is a concept that I just want you to have. Notice how on those lines you have both phases in equilibrium. So that's a take home. Anywhere on that line you could draw this diagram. You've got a meniscus, you've got liquid phase and gas phase. Anywhere on this line, you would have this situation. You've got liquid phase and solid phase in equilibrium. Down here, you have this one and this one combined. You've got ice and water, liquid and gas, all at that triple point. Now let's talk about this relative humidity and why it feels so darn hot in Huntsville. Our bodies are made to where when we sweat, the liquid is supposed to evaporate. So going from liquid to gas is endothermic, and that takes heat away from our body. If it's a really humid day, we're coated in water, and water's an insulator. And so it's not able to evaporate. And so a humid day just feels really, really hot. And so this is from the National Weather Service, and then they've got this thing called the heat index. Okay. And this is combining the temperature of the day and what it feels like with the humidity equation. And this is not going to be tested. This is just something that I want you to know about. So like if it's a 94-degree day, that's pretty hot. But if it's 60% humid, it feels like 110. And that's in this orange region. That's where you could get heat exhaustion if you're outside working a lot, okay, or possible heat stroke. If you get up here, let's say it's a 100-degree day, at 60% humidity. We're at 129. That's the heat index number. It's ridiculous. Okay, and that's heat stroke is highly likely if you're out there in a long period of time. If you're putting on shingles on the roof on a 100-degree day with 60-degree relative humidity, you better be in shape and you better drink lots of water. Okay, because you're in great danger of getting heat stroke. So this relative humidity, how does that thing work? Well, that is the actual partial pressure of water divided by the max partial pressure of water. And this right here comes from that PT phase diagram curve. PT vapor pressure line. Okay.
So I have a question.
Yes.
The triple point, is that why I never drink a cup of ice water and breathe, and then there's
That's probably just the condensation, like you see your breath or whatever. Yeah, it's if the temperature is cold enough to form like micro droplets of water that will scatter light, so then you can see it. Like on a cold day too, there's so much water in your breath that when it gets cold outside, the air temperature, you breathe out and that water can condense and create a fog. So those are water droplets, but they're so small. They're maybe a few thousand molecules. But that's enough to scatter visible light. And it appears white because it scatters all the wavelengths. So it's probably around 1,000 nanometers. It's got to be bigger than 400 to 700 nanometers, which is the wavelength of light. So when you get up to around 1,000 nanometers of a cluster, like a water drop cluster, that will scatter all the wavelengths of light and it'll appear like white fog. But it's a partial pressure of water thing. So in your breath, you have a high partial pressure of water. And that's that vapor pressure curve. Now, this is a different substance. How do I know this is not water? The slope of the solid liquid line, okay? So this, can you spot the difference? It's this one right here. That's a positive slope, okay? And that's what, I guess, normal substances are. Okay, they have that positive slope for the solid liquid line. Now let's focus in on what happens when we go from an ideal gas to a real gas. Okay, so for an ideal gas, this PV equals nRT. It equals a constant. Okay, and so if P goes up, V goes down, and we have these isotherms. We have these curves for an ideal gas. Okay, we don't have condensation. But what happens if the gas condenses to a liquid? So here we're compressing that gas, the pressure is rising, and when we get to the vapor pressure of that liquid, we start to form water droplets, or let's say this is water. We start to compress gaseous water. We're sinking the heat, so we're taking away the heat, and we're compressing it, and we reach the vapor pressure of water at that temperature, and we start forming a liquid. And so as we're compressing this system, all we're doing is turning the gas into liquid, and it has the same vapor pressure. So we're just squeezing until we squeeze all the gas into the liquid state, and now we're pushing on the liquid. So we'll eventually hit a point where we've squeezed all of the gas into the liquid state, and now if we try to press on it, we're pressing on the liquid and trying to shrink the liquid, and liquids are not very compressible. So it takes an enormous amount of pressure, you get enormous amount of pressure change with tiny little volume change. So you squeeze it just a little bit more and the pressure shoots up. Okay. This incompressibility of the liquid, by the way, is how our hydraulics work. And so we can push on this part of the liquid and it'll go through a hose and push a piston. And you look at all of your heavy equipment, backhoes and everything, those pistons on there are driven by hydraulics. We just pump liquid in there, and liquid is not compressible, and so it pushes that piston and makes the buckets work and everything like that. Okay. Gases wouldn't work as well because gases are compressible. So if I had that line filled with gas and I'm trying to scoop something with a backhoe and I turn on the gas pressure, it pushes that piston, but the gas just absorbs a lot of the pressure. Okay, and it's too squishy. but liquids are not squishy. So this is the phase diagram. This is a PV phase diagram. I just included this one again for what we call enrichment. You're going to be tested on the PT phase diagram. But let's look at the PV phase diagram because it's a phase diagram as well. This is for CO2. These are isotherms. So this will be like an ideal gas. So 334 Kelvin, ideal gas. Notice if I start adding in the intermolecular attractions, this is the actual 334. And this is the ideal gas isotherm. Notice out here, the actual and the ideal are pretty close. But as I get to smaller volumes and higher pressures, the gas starts to interact with the other gas molecules and it becomes less ideal. It starts to see attractions. If the gas molecules are attracted to each other, we should see lower pressures because they're not hitting the walls with as much strength. And so that's what we see. Here's the ideal gas, and here's the pressure at that volume that we actually measure. So we're pretty far off. And that's from the attractions of those molecules to each other. Okay, so this region out here to the right, the large volumes, lower pressures, that's the gaseous region. Over here on the left is the liquid region, so it's kind of color-coded for you. And now this has this really strange curve in the middle. This is the gas volume and the liquid volume, and this is the vapor-liquid equilibrium region. So the vapor vapor-liquid equilibrium region. Look what happens to that isotherm. So if I'm coming in here, I'm pressing on it. Here, at this point, liquid starts to form. And so this is the volume of the gas. This is the volume of the liquid. And so we form those liquid droplets. And if I keep compressing on it, all I really do is just change the proportionality of the gas and the liquid till I get to this volume. And now I'm just pressing on just the liquid, and this is that steep rise of the non-compressible liquid. So this line straight across is the vapor pressure of CO2 at 243 Kelvin. And this line is the vapor pressure at 274. So I just wanted to show you this phase diagram so you can see those horizontal vapor pressure lines. It kind of looks like that heating curve too. You know how the temperature didn't change until all of the gas was condensed or all of the liquid was boiled away. So that's where we can get the vapor pressures of these liquids from both the PV and the PT phase diagrams. So let's see how these are related to each other. Over here we have the PT phase diagram. Pressure versus temperature. We have all of the lines that we're familiar with. We have the solid, liquid, gas. We just covered that, okay? And this is the PV phase diagram. So we have the pressure, volume phase diagram. Okay, and this is all, both of those combined. And that's a confusing figure, so I 3D printed it for you. Okay, so I'm going to pass these around, and you can look, you can see it from this direction. That's the temperature here and the pressure. So the PT phase diagram. You turn it this way, that's pressure versus volume. That's the PV phase diagram. And so this is the 3 state variables for water. So I know, give me temperature, pressure, and volume, and I can tell you what state it's in. Okay, so that's why that's called the equation of state. It's, you give me 3 variables, PT and V, and I can tell you what state it's in. And so it's a 3-dimensional surface. It doesn't get any more complicated than 3 dimensions, thank goodness. So we have pressure, temperature, and volume. And the states are governed by those 3 variables. So even though this seems really complicated, we're done. We got all 3 variables, pressure, temperature, volume. Here's the equation of state for water. So let me pass these around. This is my old 3D printer, the orange one, and my new 3D printer, the black one, and it's way better. Okay. Way more kids. Okay. Let's go back one and look at those gas volumes so that you could figure out the density of the different gases too. Like this is the volume of a particular of this gas at CO2 at 258. You've got the vapor pressure. This is the volume. You've got the temperature. This is the molar volume. So that's the volume of 1 mole. Okay. This is the volume of 1 mole at 258 of liquid. Now let's talk about the critical point. There is a temperature above which you don't have this vapor-liquid separation. So notice how if I'm in this region right here and below, this whole region here, you've got, if that's in a container, you've got a meniscus. Because I've got a liquid and I've got a gas, okay? This container represents everything down in this region. But if I'm up here in this region, in the green region, I'm in the supercritical fluid region. It has some interesting properties, and that's why we talk about it. There's really no definite line. There is a definite temperature. So if you've got to be above that temperature, but you also have to be below the volume, the critical volume. So right here would be VC. And you've got to be above the critical pressure, PC. So those are your 3 state variables: the critical temperature, critical pressure, critical volume. If you're in a smaller volume, higher pressure, higher temperature, you're in a supercritical region. Super just means higher than, right? Supercritical, so it's higher than the critical temperature. And the reason it's interesting is that it has the density of a liquid, but it flows like a gas, like through tubes and stuff like that. And it has no meniscus, so it completely fills the whole container. Whereas over here, the liquid, if it's, the liquid is down in the bottom of the container and the gas is at the top. And so they're starting to move towards using supercritical fluid for some cleaning operations like dry cleaning. So they could use supercritical CO2 to dry clean your clothes. You just throw your clothes in there, stack it all the way to the top, and then they start pumping CO2 in there and raising the temperature. And when they get to the supercritical fluid, it's a really dense liquid made from a gas. And it's not all down at the bottom of the chamber, it fills the whole chamber. So up here, the supercritical fluid, we can draw one of those little piston diagrams, and there's no meniscus. Okay. I'll just call it SC, supercritical fluid. So if I have clothes all the way to the top of the container, it's going to clean the top, close at the top just as well as it cleans the clothes in the bottom. Okay. Now, what would make CO2 a good solvent? Well, it's nonpolar. And if I have a grease stain on some fabric that I don't want to get wet with water, I could take it out with CO2. And that grease would dissolve into CO2. I pop a valve, flow it into another container, it takes the grease with it, and then I change the pressure, drop the CO2 out as a gas, and the grease falls to the bottom, and then I can throw it away. Here are the critical constants of a bunch of other gases. Down here is CO2, so we talked about the critical temperature at 304, okay, Kelvin. So that's pretty close to room temperature. 298 is room temperature. So we don't have to heat CO2 up very much to get it to be at least possible to make a supercritical fluid. So when we get over 304, it's possible to make a supercritical fluid out of CO2. We have to squeeze it pretty good. We have to get it to 94 milliliters, so that's 0.094 liters per mole. Okay, so think about a mole of an ideal gas. Remember we did at STP all the time? A mole of ideal gas at STP was 22.4 liters. We got to squeeze this down to 0.09 liters. And we got to crank up the pressure to 73 atmospheres. Who has a calculator? Can you calculate 73 times 14.7? Let's get PSI, because I think of PSI. 73 times 14.7. 1,070. Okay, 73, right? So we got to get above 1,000 PSI. You squeeze it in a small container, 1000 psi, warm it up a little, and you have supercritical CO2. What about, yes.
Sorry.
Yeah, that's great. Yeah. Water. I mean, here's water. We have to really heat it up, 647 Kelvin. So we've got to really crank up water to get it to be supercritical. 218 atmospheres, and we have to squeeze it down to 0.055 liters. So look at hydrogen. Hydrogen's critical temperature is 33 Kelvin. So we're above that. We're so far above that, you're not going to see liquid hydrogen running around at room temperature, okay? And yet we're trying to fill Artemis. This Artemis 1, are you following that? But the moonshot, they're going to send an unmanned spacecraft around the moon. Their hydrogen line keeps leaking. They have to pump hydrogen, liquid hydrogen, at temperatures below 33 Kelvin. So you have a refrigerator hooked up to a refrigerator, hooked up to a refrigerator, hooked up to the hydrogen. And you cryogenically cool it down, and you have insulated lines, and you pump it in there. If you have any hot spots in there, then it can form a leak and come out. Okay. So let's test our knowledge of the various phase diagram areas. So this is the first Kahoot we've done in this class. If you would like for me to sort of track your participation, use your SHSU, 3 initials, 3 numbers, and then I can match it up just to kind of see how you did on the Kahoot. That's not required, but it's always nice for me to kind of see how you're doing. Okay. You don't have to have the app. If you have the app, that's great, but you can just go to kahoot.it and type in the game code, which will come up here in a second. I'm going to swap this around. I'll get you the game code here in a sec. Okay, there he goes. Okay, so there, 552775 is the game pin. Get too creative with the names, I'm going to cut you out.
What is so creative?
Yeah, nothing obscene. Whatever I think is obscene. And we've got some time for me to reteach if there's some things that confuse you on this. So. Yes? Oh, really? It looks like it dropped out already, so go ahead. Okay, y'all as a group got to kind of tell me when to go, because I don't... Why does it do the little jumpy thing? I don't know. That's new.
Good question.
Yeah. Anyone still trying to get in? Okay, let's go before it starts dropping people out. I think you can still jump in if it's going. Okay, which letter is in the gas phase region of this PT phase diagram? Can you see it? Oops. Game pin down here, if you get dropped out, is 552775. And out of time. Okay, very good. Very good. So here's what we're looking at. A, B, and C. Which one was the gas? Okay. So it was C. Okay. Which letter's in the solid phase? And you get points for being fast and accurate. So, but you can still hit the wrong one if you try to rush too much. Ah, very good. I'll take a picture of it, the whole class, if you get 100%. So this is the phase diagram. Which one's which? All right, what do you think we're going to do next? Okay. Which letter's in the liquid region? Get your thumbs ready.
Okay, guys.
Yeah, that's great. What am I getting a text about? Okay. Do we have anybody still left? Almost.
Oh.
Almost. Yeah. All right, yeah. So A is solid, B is liquid, C is gas. All right. What else can I ask you? Let's see. What process is happening when water drops appear on the side of my iced tea glass? Is my glass leaking? Oh, so close. Condensation. So that's condensation on the outside of the glass. Okay. What is the process when dry ice, which is solid CO2, bubbles vigorously in water? This one's kind of tricky. The water is really acting like a temperature bath. And it's pretty cool. So then you can see the gas coming off the solid. And we're out of time. All right, so that's sublimation. So the CO2 is solid and it's going straight to gas. We put it in water just so we can see it happening. Okay, it's cold, so that's why you get all the smoke. So the water vapor forms those little micro droplets, which we call fog. And so that's really cool. Has everybody seen that? I need to bring some to class sometime. One year we did a National Chemistry Week demo on, out in the mall area, and we had a container with CO2 and water, and it was bubbling, and a student had never seen it before, never even thought of it before, and they were looking underneath the table, and they're looking at it, and they're like trying to get close to it, but didn't want to touch it. And when I said, "What are you doing?" He's like, "What's making this boil?" Like they thought we had a heat source under there and it was boiling water, and it wasn't. It was CO2 and water, and they had never seen it before, so you can't assume. Anyway, it was pretty exciting. We also had a lead brick there, and they're like, "What's holding this down?" Yeah. Okay, what is the process when water is boiling? Do we have another name for that? Oh, so close. Vaporization. Yep. Sublimation would be going from solid to gas directly. So, all right. 7 of 10. What process makes ice crystals grow on packages in your freezer? All right, that's deposition. So freezing is going from liquid to solid. And so since this is going from gas directly to solid, it's the companion to sublimation. So sublimation is solid to gas, deposition is gas to solid. Okay. Number 8. What is the normal boiling temperature of this substance? So you have to pick a letter that corresponds to the normal boiling temperature of this substance. So we see 1 atmosphere is the dashed line that goes across left to right. Okay, so letter G, let me show you the plot. So here, the normal boiling, so 1 atmosphere, this would be the normal boiling point right here. When the vapor pressure line hits 1 atmosphere, that's the temperature at which it's boiling. Okay, number 9, what is the freezing temperature of this substance? This red one is C and the orange one is G. It's kind of hard to see. And then F and E.
Oh, wait. I'm sorry.
Yeah.
Sorry.
Okay, so it's letter F. Let's find that. So it's down here. It's letter F. Again, a temperature, a boiling temperature or melting temperature is going to be that x-axis where it crosses that x-axis. Okay. And number 10 coming up. Last one. What is the critical point of this substance? So where on the phase diagram are you going to find the critical point? Pick the letter closest to it. Okay, so majority got it. It's up here, letter C. What is E? Other people put E. What is E? Triple point. And you see that because there's 3 phases touching at that point. So that's the triple point. All right, great job. You can see the little dancing podium while you put up your stuff. Okay, so good job, 9028. That's your score. Kiki, AMC, and the top score, 9,229. Very good. We'll see you Friday.
That was fun.
Good.